Hello everyone, my name is Anna Fryan. In this presentation, I am going to talk about one of my projects in predictive modeling. The name of the topic is Predict the proportion of death in a particular race suffering from certain genitourinary diseases based on year and age group. Let us first understand what I mean by genitourinary diseases. Genitourinary diseases involve disorders of the genital and urinary organs that includes kidney, bladder, ureter, and the urethra. It also includes the prostate in males, ovaries, and uterus in females. Therefore, any disorder involving these organs are classified under genitourinary diseases. Let me explain the data I have used for my predictive modeling. I obtained the data from Centers for Disease Control and Prevention, CDC for short. The data is a combination of 4 datasets, each dataset representing a particular race. I am using R for my analysis. After data cleaning and data manipulation, such as sorting the data by year, race, and age group, I have obtained 4 variables to predict the number of deaths. The year variable goes from the year 1999 to 2018. The race variable has 4 levels: white, American Indian, Asian, and black. The age group starts from the age of 1 and goes on with an interval of 5 years. Therefore, the first age group is 1 and below 1. The second age group is 1 to 4. The third age group is 5 to 9, and so on. There are 258 causes of death classified under genitourinary diseases such as urinary tract infection, acute renal failure, acute tubulointerstitial nephritis, etc. My initial goal was to predict the total number of deaths based on race, age group, cause of death, and the year. For example, what would be the number of deaths of African American in the age group 80 to 84 suffering from urinary tract infection in the year of 2021? Such question can be answered through my predictive model. I would use gradient boosting model to predict the number of deaths from genitourinary diseases. Gradient boosting model has high predictive accuracy and works really well with categorical and numerical values. Therefore, this model is a good fit for my data. I would train the model on 80% of my data, then predict on the rest 20% of the dataset. Then the difference in the real number of deaths and the predicted number of deaths would give me my predictive accuracy. But what happened when I predicted on the 20% of my test dataset? Just looking at these two graphs, I can tell that the predictive accuracy is lower than I have expected. The predicted versus observed graph shows that for higher number of observed deaths, the model is underpredicting the number of deaths from genitourinary diseases. An accurate model would have data points closer to that diagonal line. We can see the same from the residual versus predictive graph. An accurate model would have data values close to the zero line. The predictive accuracy value, in this case the R squared value on the test set, is 63.85%, which tells that my model is able to explain only 63.85% of the variability in the test set. I think this is a low accuracy value and needs resolving. I consider anything above 75% to be accurate, but why is the accuracy of the model so low? This is because the model is not considering the total number of deaths relative to the population in each age group of a particular race in a particular year. Therefore, I believe the ratio of deaths to the population in each category would give a better predictive accuracy. Therefore, my final goal is to predict the ratio number of deaths by the population based on race, age group, cause of death, and the year. As you can see, the dataset now has a population column which changes with race, age group, and year. I got a new column called death ratio by taking the natural log of the ratio of deaths by population. I've used the natural log because the number of deaths is very small compared to the population, which would make the ratio close to 0. The model would not predict well with a value close to 0. After transforming, we can see that the death ratio is a number far from 0, though in the negative. I would have to reverse transform the predicted value using the exponential function after my prediction. The predicted versus observed and the residual versus of predicted graphs looks much better. The negative values on the x and y axis is just from the natural log transformation. The data points are concentrated along the diagonal of predicted versus observed graph, showing that the model is predicting accurately on the test set. Now we can see that the model is able to explain 79% of the variability in the data of the test set, and I consider it to be very accurate. Now let us see which variable had the most influence on the prediction. First, let's define variable importance. Variable importance shows the relative influence of each variable in the model. But why does the race white has the most influence on the model? This is because the race white has the most data compared to all other races. To confirm this, I would like to see what is the total number of deaths in white population compared to the total number of deaths from genitourinary diseases in 2018. Here we can see that the race white had the most deaths when comparing it to the total deaths from genitourinary diseases. But that is not a fair comparison since different races would have different population count. That's what made the accuracy of the first model low compared to the second. For example, in 2018, 50 white people died of genitourinary diseases in a certain area, and the total white population in the area was 1000. On the other hand, 25 black people died of genitourinary diseases on the same area, and the population of black people on that area was 100. Then, just from the number of deaths, more white people died from genitourinary diseases than black people in that area, but the number is just misleading. Rather, the ratio of death to population would give a better idea regarding the fatality rate among the races suffering from genitourinary diseases. If we do that, then we see that American Indian people are the most fatality prone from genitourinary diseases, while white people are the least fatality prone from genitourinary diseases. Now let's see which age group is the most fatality prone. Age group 80 to 84 is the most fatality prone from genitourinary diseases. Which genitourinary disease is the most fatality causing? We can see that vesico-intestinal fistula is causing the most fatality. Now let us predict with my model. Let's predict how many African American will die in the year 2021 from urinary tract infection in the US. The model predicts a death to population ratio of 7 into 10 to the power negative 6, which means 7 out of 1 million African American people will die from urinary tract infection in the year 2021 according to the prediction given by my gradient boosting model. So, what is the importance of the model? My model can be used to target healthcare solution to people of age groups who are fatality prone from genitourinary diseases. It will also help to target healthcare solution to people of certain race who are fatality prone from genitourinary diseases. It will help predict who will be the fatality prone from genitourinary diseases and provide healthcare solution according to the prediction from the model. Thank you. If you have any question, please feel free to mention it in the comments.